What's up, geometry? Thanks so much for tuning in for another episode of Math with Mullins. Today we're going to be talking about lesson 2.1, but now we're going to switch it and talk about the conditional statement sides. This is technically day 2. We talked about day 1 yesterday with conditional statements. Now we're going to look at what are biconditional statements and what can we do when we use truth tables. We do have a lot of writing today, so you're going to see me typing a lot on the screen, but some of the things will also be drawing on the screen for us. First thing we want to fill in is what is a biconditional statement. So that's the first thing we're filling in our notes. A biconditional statement is a single statement written using if and only if. So a lot of the times we can see it like this. P happens if and only if Q happens, or you can also write it with the symbols P and then the double-sided arrow leading to Q. We want to write that down for the words and the symbol parts. So when you're done with that section of your notes, you can click play. But for right now, let's pause it and just understand what a biconditional statement is. That just means P will always lead to Q and Q will always lead back to P. So the next thing we're going to do is rewrite each of these definitions as a single biconditional statement. And what I'm going to try to do here is type on the screen using a text box. So bear with me. But it says if two lines intersect to form a right angle, then they are perpendicular lines. So we would write it like as such. Two lines intersect to form a right angle if and only if they are perpendicular lines. So notice how I wrote the if and only if, okay? The next one, if an angle is a right angle, then its measure is 90 degrees. So an angle is a right angle if and only if it is measuring 90 degrees. The third one we have, if two line segments have the same length, then they are congruent segments. So again, using that if and only if statement, two line segments have the same length if and only if they are congruent segments. So really you're just connecting these two statements with the terminology if and only if. Again, we're going to try that with a few more examples. Rewrite the statements as a single biconditional statement. If Mary is in theater class, then she'll be in the fall play. And if Mary's in the fall play, then she must be taking theater class. So we would write this as a biconditional statement as the following. Mary is in the fall play if and only if she is taking theater class. Okay. The next one says, if you can run for president, then you are at least 35 years old. And if you're 35 years old, then you can run for president. So again, these sound very redundant, but we're again just getting into the habit of how to write a biconditional statement. So you can run for president if and only if you are at least 35 years old. And then you do want to make sure that you spell president correctly. There you go. I spell it right? Yep. Okay. So that's what I have there for rewriting those biconditional statements. The next thing we're going to talk about is a truth value table and how those work. So the truth value of a statement is either true or false. And we talked a little bit about that in our previous video. You can determine the conditions under which a conditional statement is true by using what we call a truth table. So this table right here has P being one aspect, and then Q being another aspect, and then P to Q. What does that make? So if P is true and Q is true, that means the whole conditional statement is true. But if P is true and Q is false, then the whole thing is false. If P is false and Q is true, then it has to be true for that conditional statement. But if P is false and Q is false, then the whole entire thing is true. This will all make sense in just a moment when we actually put some statements to it. Right now, it just seems kind of randomized, like why are these true and why is this only one false? Okay. The conditional statement P to Q is only false when a true hypothesis produces a false conclusion. Let me read that one more time. The conditional statement P to Q is only false when a true hypothesis produces a false conclusion. So that's where we see it right here. Okay. A true hypothesis is concluding a false statement. Two statements are logically equivalent when they have the same truth table. So that just means we want to be able to prove that using truth table. So using the truth table to make truth table, use the truth table to make additional truth tables for the converse, inverse, and contrapositive of a conditional statement of P to Q. So this is where we're going to have a little bit of time of drawing. So the first truth table we're going to talk about is the converse truth table. We have P, Q, and then P leading to Q. I want you to understand something, that whatever we put in this first column is going to be considered the conclusion, and the second column is the hypothesis, similar to what we saw in the previous day's lesson. Okay? If P is true and Q is true, then that will be performing a true statement. And I just realized that I accidentally did P to Q, and this actually should be Q to P, because remember we talked about converse statements as reversing the statement, like if today is Friday, then tomorrow is Saturday. The converse of that would be if tomorrow is Saturday, then today is Friday. So you're just reversing that. Okay. For converse statement, if P is true, but Q is false, then Q to P will still be true. Okay. If P is false, but Q is true, then that will make a false statement. But if P is false, the conclusion, and Q, the hypothesis, is false, then Q to P will be true. Okay? The next one we're going to talk about is the inverse truth table. All right, so for the inverse table, we're going to have P, Q, not P, not Q, not P leads to not Q. And this idea, not P would now be the hypothesis, and not Q would now be the conclusion. Okay? Here we go. If P is true and Q is true, that means not P is false and not Q is false, which would make the entire inverse statement true. If P is true and Q is false, that means not P is false, not Q is true, which would make the entire statement still true. If P is false and Q is true, not P would be true, not Q would be false. The not P, not Q statement would now be false. And if P was false and Q was false, that just means not P and not Q would both be true, which would make the whole entire statement true. Hopefully seeing this inverse table is helping you understand why the converse table also works. Okay, we do have one more table we're going to draw down here, and that one is going to be the contrapositive. So here's our contrapositive table. Again, we have P, Q, not Q, but remember contrapositive is the opposite of the inverse, so that final column is what's changed. Not Q is leading to not P. Here we go. If P is true and Q is true, not P and not Q are false, that means not Q to not P is true. If P is true but Q is false, that means not P is false, not Q is true. That means the entire contrapositive statement would be false. If P is false and Q is true, that means not P is true, not Q is false. The entire statement is true. And squeezing this in right under here, if P is false, Q is false, not P is true, not Q is true. So to get from not Q to not P would be true. And just for a reminder, I forgot to mention to you, not P would be the conclusion, and not Q would be the hypothesis. Okay, I ran out of room at the bottom though, so you can put that up there at the top. So what we're going to do is talk about how to make a truth table for the conditional statement of P to not Q. So we're going to do that very similarly how we did before. Start with P as one column, Q, not Q, and then how do we go from P to not Q? Okay, if P is, true, and Q is true, not Q would be false. So P to not Q would be false. Okay, if P is true and Q is false, not Q would be true. So from P to not Q, that would also be true. If P is false and Q is true, not Q would be false. So from P to not Q, that would be true. And last but not least, if P is false and Q is false, not Q would be true, and the whole entire conditional statement of P not Q would be true. Okay. Make a truth table for the conditional statement not parentheses P to Q. So this is just going to mean that parentheses would be distributing the not P to not Q, okay? Which might end up looking very similar to something we've already talked about. All right, so here we go. We've got our P and Q table printed out, and now we're going to talk about the differences in true and false. If P is true and Q is true, P to Q would be true, but not PQ would be false. So whatever this statement is will just be the opposite for here. If P is true, but Q is false, P to Q would still be false, which would make the not P to Q statement true. If P is false, but Q is true, the statement P to Q would be true, but the not P to Q statement would be false. And if P was false, Q is false, the P to Q statement would be true, but not P to Q statement would now be false. Okay? These may still be a little tricky to understand, so what we're going to do is represent each one of these using conditional statements, converse, inverse, and then contrapositive in words. So we're going to type on the screen for these. We're going to start with conditional, which is P to Q. Okay? If snow is falling, then it is winter. Okay, and these are statements that you can use to also maybe understand the truth tables. For the converse statement, remember that is Q to P. If it is winter, then snow is falling. Okay, converse just means switching around Q and P. Then we have what's called the inverse. Remember, this one is not P leading to not Q. If snow is not falling, then it is not winter. That would be true in some cases, but false in others. So we would consider that to be entirely false. And then we have contrapositive, which means not Q is leading to not P. If it is not winter, then the snow is not falling. And that is our true statement. Okay? That is the conclusion of our notes for today. Hopefully the truth tables, if they did confuse you at all, then maybe think about what is a true statement. If snow is falling, then it is winter. Use those to relate back to the truth tables, and those should make sense a little bit more. Thanks so much for tuning in, and I hope you have a great day.